In this third video, Mark Bohr describes what he believes will be the future of Moore's law and what it will entail. Mark's fourth era of Moore's law is marked again by rising difficulties and making transistors smaller. So new ways of scaling need to be developed to keep device density rising. This includes new layout techniques, or something Mark calls hyperscaling. That helps pack more transistors into a given area. The other is a collision of electrical and economic realities. The electrical reality is that to keep improving compute performance per watt, memory has to be brought closer to the processor. In the past, that was done by adding cache memory on chip. But this has reached its limits, and even more memory is needed. The economic reality is that added complexity of putting all this onto a single chip makes the cost of the chip unviable. Both collide to push the need for heterogeneous integration. By the way, the last in this video series will follow this video, Mark Bohr's Rules of Innovation, where he describes the lessons he learned about innovating at scale. But for now, let's hear what Mark has to say about the coming scaling and heterogeneous integration era. So let's move on to the future. The scaling and heterogeneous integration era. How is that going to change things?
That's my name for what I view as the next era, as we move out from just the power-constrained era. Now we're facing the dilemma where to get the very best system performance, you need to combine a lot of different functions, features that aren't always doable on the same technology. The system needs both high-performance computing, it needs low-power computing, it needs memory, it needs some analog and communication technology or circuits. You can't put all those efficiently into one piece of silicon. So it's better to break it up into more specialized chips, different technologies that you can combine together in some very dense package. So system integration is still our goal, but now within a package using chip stacking techniques.
If we rewind all the way back to the beginning of time for semiconductor, for the integrated circuit, right? There was this debate between the noise circuit, which everything was on a single chip, using the planar process. And then there was the Kilby method, which was what we would call 2D packaging today, where you wire bonded individual transistors together. Although today we're wire bonding different processes. Why is it working today and it didn't work back then?
Well, I think the main reason it's working is some new innovations, such as Intel's latest Foveros chip stacking technology, where we can combine different chips in one package, chips from different technologies, maybe combining a 14 nanometer chip and a 10 nanometer chip, or maybe a memory chip and a logic chip together into one small package with very dense interconnects between them. If you try to do that outside the package, in other words, a memory chip over here on the motherboard, a logic chip over there, you have a fairly inefficient bus between the two, which is becoming more and more critical to overall system performance and power. So bringing those chips together with a high density of connections in one package is a very powerful tool for delivering improved system performance and power.
Right, and before we were trying to get high density of transistors, back to your model for memory of scaling. Now you're still in this power constraint, right? But we're no longer in a power constraint for just the chip itself.
Yes. Yep.
It's
But now I think the game is to try to pack as many transistors, not per square millimeter, but now per cubic millimeter, by stacking them.
Yeah. And again, that's not a technology that's brand new, right? I mean, I remember Intel working on in secret working on TSV technology probably 20 years ago, right?
Well, we've been working on TSV technology for a while, but there are some other unique aspects of Foveros that haven't been fully disclosed yet that really enable a much denser set of connections between the stacked chips.
Right, but for me the point is that you don't introduce a technology until it's ready for manufacturing.
That's a good point, and there are two aspects to that ready. Number one, there is a significant market advantage in doing this. It's not a minor advantage; it's a big advantage. But also that it's manufacturable. So yes, we have a very manufacturable TSV technology and a very manufacturable chip stacking technology in a compact package.
And it has to be cost effective.
And cost effective. So even if the engineers don't do it, our managers will. They'll count the pennies and say this is either too expensive or no, it makes good economic sense.
We're going to pause the conversation right here. Please look for the upcoming continuation of it in the near future.